Okay, Bismillahirrahmanirrahim. Right, so this is the rate concentration graph for a 0, first, and second order. Sorry, let me just mute all of you. I'll unmute you again later. Okay, so it's easy to see for the 0 order. It is a horizontal straight line. For the first order, it's an increasing straight line that passes through the origin. And for the second order, it's an increasing curve. Okay, so putting them all together in the same graph looks like this. Now remember, this particular order is only with respect to one particular reactant. Okay. The next one is the concentration time graph. Now, concentration time graph is a little bit tricky for the first and second order. Now, for the 0 order, it's quite obvious because it's just a decreasing straight line. Okay. Now, please let me know if my audio is broken because Zoom just notified me that my connection is unstable. I don't know why that's happening to me today. Okay, now going back to this graph, the reason why the concentration time graph for a 0 order is a straight line is because no matter how much I change the concentration of my reactant, my rate will be the same, gradient. Okay, in a concentration time graph, to find the rate, you have to find the gradient first. So it is not as straightforward as your rate concentration graph. From the rate concentration graph, you can just read it off. What happens to the rate when you double the concentration? What happens to the, But for concentration time graph, you need to find the gradient in order to know the rate. Okay, why is it the gradient? Because change in concentration, which is your y-axis, over change in time, which is your x-axis. Okay, so for the first and second order, both of them are decreasing curves. The reason why they decrease is because we are talking about reactants. Over time, as the reaction proceeds, the reactants get less and less. Okay. So that's how you find the gradient in a curve, whether it's first order or second order. The third method of finding the orders of reaction graphically is by calculating the half-lives. Okay, half-life is the time taken for your concentration to go down by half. Okay, that's why the symbol is T1/2, T half. Right. The easiest one to remember is your first order will have a constant half-life, and only for first order you are able to use this formula, okay? Because your T half of a first order is constant, it's the same. You can also use formula for the other orders, but it's a little bit more complicated and it's not required for your syllabus, okay? And then we looked at finding the half-life graphically, okay? The half-life, again, is the time taken. So you should be reading the x-axis, okay? Because we want to know the time taken for the concentration to go down by half. So from 4 to 2, this is the half-life. From 2 to go down by half, which is 1, is this section only. You do not start from 0. Okay, because if it's from 0, that means the concentration drops from 4 to 1, which is not half. Okay, and then further, when you decrease the concentration of your reactant from 1 to 0.5, that is your half-life. Okay, that portion. Again, it's not from 0. And then you saw that the half-life for the 3 successive half-life, this is called successive half-life because it's continuous. Okay, from 4 to 2, that's your first, 2 to 1, that's your second, 1 to 0.5, that's your third. So that's what we meant by successive. And you found that it was approximately 17 minutes, 17.5, and it's again approximately constant. Okay, when you look at this graph, you should automatically reject that it's a 0 order because 0 order would have been a straight line. Right, moving on. we can also find orders of reaction experimentally. That's to say from experimental data. Okay, well, usually they will give you the initial rate. Now you already know how to find the initial rate of a reaction. You can find the initial rate from a concentration time graph. Okay, concentration time graph, and initial rate is when you draw a tangent at t equals to 0. Now you may argue at t equals to 0 the reaction is 0 because the reaction hasn't started. Now what we mean by that is the rate of reaction just after 0. Okay, so that's the tangent, and the tangent gives you the rate. Right, how do we find the orders of reaction experimentally? Say you do not have any data, and then you are given an experiment to carry out. You are to investigate, okay? So we can do a series of experiments where we can start changing the concentration and we find the rate. Because after all, we just need these two variables. What happens to the rate as we change the concentration, okay? But now, you know that in a reaction, there are sometimes more than one reactant. And the order of any particular reactant is specific to one reactant at a time. So you have to investigate them one at a time. Okay, so to do this, we work out the rate equation. We do a series of experiments where the initial concentrations of reactants are changed one at a time, and then you measure the initial rate. Okay, now let's use this equation, this reaction, for example, where we have a hydrogen gas reacting with the nitrogen monoxide. So the question wants you to come up with the rate equation. Okay, now in order to know the rate equation, you need to know the order with respect to particular reactant first. What is the order of hydrogen? What is the order of nitrogen monoxide? They do not have the same order. They can have the same order coincidentally, but you need to investigate one by one, right? So if we want to find the order of hydrogen, that means you want to know how changing the concentration of hydrogen will affect the rate. Okay, to find the order of hydrogen, you have to carry out a few experiments that vary the concentration of hydrogen only. Okay, so you do the first experiment, you start with a certain amount of hydrogen, you start with a certain amount of nitrogen monoxide, and then you measure the rate. Okay, and then you carry out a second experiment, still using the same reaction, but this time you change the concentration of hydrogen. The easiest way to do is to double the concentration of hydrogen. Okay, you double the concentration of hydrogen, you keep the concentration of nitrogen monoxide constant. Because if you change two variables, then you cannot study the effect of changing the concentration of hydrogen on the rate. Now you have two changing variables, which is different, okay? If you're interested to find the order of hydrogen, you only change the concentration of hydrogen. And then you compare the value of the rate of these different experiments, right? Okay, that's that. If you want to find the order of nitrogen monoxide, same procedure happens. To know the order, you want to know the effect of changing the concentration of nitrogen monoxide only on the rate. So this time you will keep the concentration of hydrogen constant and you change the concentration of nitrogen monoxide at different experiments. Okay, and then of course you look at the rate. Right, an example on how to do that. We look at a particular example. Okay, so this example 1 is looking at this reaction where you have a reactant A plus B plus 2C to form D plus 2E. Usually we're interested in reactants only. Okay, using the initial rate data in the table. In order to calculate the order for a particular reactant, it is easiest to compare two experiments where only that reactant is being changed. Okay, so this is just to remind you what a 0, first and second is. 0 is doubling the concentration has no effect on the rate. First is doubling concentration, rate doubles. And second order is doubling the concentration, rate goes up by 4 or quadruples. Okay, so this is a set of experiments that have been carried out. Okay, so this is what I mean. If we look at experiment 1 and experiment 2, experiment 1, you choose the nice numbers for your reactant A, reactant B, and reactant C. Okay, when you let them react, you find the initial rate. Okay, you just find the initial rate of this reaction. How do you find the initial rate? From the concentration time graph of any of this. Okay, right. So you found the initial rate, and then you repeat the same experiment. You start with a new experiment, but of the same reaction. Okay, but this time you change the concentration of A only, keeping your B and C the same. Again, you calculate the rate of the reaction, right? The reason for this is because you want to look at what happens to the rate when you double the concentration of A. Okay, looking at experiment 1 and 2, this enables you to study or to deduce the order of the order with respect to A first. Okay, so let's see. Hold on, I'm going to, I lost my cursor. Right, I'm gonna unmute you all because we're going to look at this question. Right, when we compare experiment 1 and 2, what can you say about the concentration of A?
Increases.
It increases by 2, it doubles, right? So you want to now look at the effect on the rate. What can you say about the effect on the rate?
Double.
It doubles as well. Okay, concentration goes up by 2-fold, the rate goes up by 2-fold. So what can you say about the order with respect to A? 0, first, or second? First order. Okay, so as the concentration of A doubles, B and C stay constant, the rate doubles as well. Therefore, the order with respect to reactant A is first order. Is that clear?
Yes.
Okay. Isa, what happened to you? Why are you late?
Sleep.
You overslept? How could you? Didn't you have registration at 7:30 just now?
Yes.
And then you went back to sleep.
Masa break.
Oh, okay, so please make sure you copy down this working on the table. Okay, next we're going to study for reactant B. Okay, and then if you look at these different experiments, the best experiment to look at is experiment 1 and 3. Why? Because for experiment 1 and 3, concentration of A stays the same, concentration of C stays the same. So this enables us to study the effect of concentration B only. Okay, so let's see. Experiment 1 and 3. The concentration of B goes from 0.5 to 1.0. That's also doubling. It goes up by 2. What can you say about the rate?
Times 4.
Quadruples, or it goes up by 4. Okay, so what can you say about the order of reactant B?
Order second.
Second order, that's right. Okay, so as the concentration of B doubles, A and C stay constant, the rate quadruples. Therefore, the order with respect to B is second order. Okay, so you need to choose your experiments wisely. You just choose 2 experiments that can help you to study the effect of changing the concentration on the rate. Okay, the last one is reactant C. Are we ready to move on?
Yes.
Okay. Now reactant C, we take experiment 1 and 4 for the same reason, because experiment 1 and 4, the concentration of A is the same, 0.1, 0.1. Concentration of B is also the same, 0.5 and 0.5. The only thing that is changing is the concentration of C, which is again double. You go from 0.25 to 0.5. Okay. Now, as you double the concentration of C, what happens to the rate?
Constant.
It's the same.
It's the same, or we call it unchanged. Okay. So the rate stays the same even though you double the concentration of C. So this tells you that C must be zero order. Are you happy with that?
Yes.
Okay, so the examples given on the notes are nice numbers. When you come to do your exercise later on, it will involve a little bit numbers that are not as nice, but still you can use your calculator, not a problem. So that means you know what's coming next. You have your exercise with you.
Homework.
Yes. Okay, so sorry, excuse me. See, this is why we need to have online classes. Otherwise, I would have sneezed in front of you, and that would have caused you panic. Right. So that is a typo. To summarize it all, the order with respect to reactant A is 1. The order with respect to reactant B is 2. And the order with respect to reactant C is 0. Now that you know this information, Eric, June, and Nick, you can write down the rate equation. Okay, the rate equation is equals to K, rate constant. You will always have rate constant in your rate equation or rate expression, times by the concentration of A to the power of 1, times by the concentration of B to the power of 2, and times by the concentration of C to the power of 0. Okay, you actually have this, but you omit it because anything to the power of 0 is just 1. Okay, so this shows you that the rate is only affected by reactant A and reactant B. Yeah, reactant C has no effect on the rate. That's why it doesn't appear in the rate equation. Okay. Hey, boys, are you listening? I hope you are listening. Boys in the group chat. Can the virus travel to the phone? Oh my God, please. Okay, so please take note of this typo. It should be reactant C being 0. No problem so far? Ready to move on?
Yes.
Okay, so we move on to the next example. Okay. So in most questions, it is possible to compare between two experiments where only one reactant has its initial concentration changed. If, however, both reactants are changed, then the effect of both individual changes on concentrations are multiplied together to give the effect on rate. Okay, so what do I mean by this? This is when you are changing more than one reactant. Okay, so there's not much information about this reaction, but I can tell you that X and Y are the reactants of this particular reaction. Okay, so they carry out 3 experiments. They started with 0.05 mole per dm cube of reactant X, and then 0.1 mole per dm cube of reactant Y, and then they measured the initial rate of reaction, and they found it to be that. Okay. Now, the first one that we can work out is reactant X. Okay, we start with reactant X. Which two experiments can we look at to study the order of X?
1 and 2.
1 and
1
2.
and 2.
Okay, so let's have a look at 1 and 2. For reactant X, compare between experiments 1 and 2. Okay, so going from 0.05 to 1.0, that's times 2.
Yes.
Okay, the concentration of Y stays the same. The rate, what can you say about the rate? It doubles as well. Okay, so this means that X is 0 first or second? First order, that's right. Okay, so as concentration of X doubles, rate doubles as well. The order with respect to X is first order. Okay, can you please copy that down? Ang, can you please make sure that you copy this down? Thank you.
Don't play with the chat.
Yes, don't play with the chat.
What? Yes.
You done?
Yes.
Ang, are you done? Ang is still in the group chat. Aiyo.
Lucky miss.
Ang, Nick asked me to block you. Okay, next. So we got that the order with respect to X is first order. How do we identify the order for Y? Because if we look at experiment 1 and 2, Y is not changing. So we're only left with 0.1 to 1 and 3 is also fine. 0.1 to 0.2. You're also changing X. You can also take experiment 2 and 3, okay, because your concentration of Y is changing, concentration of X is also changing. So this is an example where you are changing two reactants at the same time, okay? So both reactants are changed, therefore the effect is multiplied together, okay? What do I mean by that? Let's have a look at experiment 2 and 3. Now, in experiment 2 and 3, not only the Y is changing, but X is also changing. Can you see that?
Yes.
And this is possible, okay? 0.1 to 0.2 is double, okay? And then, let me use a different color. Your Y is going from 0.1 to 0.2, which is also double. So you can see that your rate is affected by both the changes in X and Y. Okay, let's have a look at your rate. Going from 0.3 to 2.4, how many fold is that?
4.
0.3 to 2.4 is 4.
8.
8 times by 8. Okay, now remember this effect times by 8 is contributed both by X and Y. Okay, now I can tell you that X is first order. We already know that X is first order, right?
Yes.
So out of 8, 2 of them times by 2 is due to the effect of X. Okay, and then you have a remaining times 4, correct?
Yes.
So I repeat this, times 2 comes from X because X is first order. You double it, you double the concentration, the rate is also double. Now, the total change in rate is times by 8. Okay, so you have a remaining times by 4. So this times 4 is the effect that you get from Y. Okay, so this is what we mean by combined effect. So times 8 is actually a combination of changing X and changing Y. You already know that X is first order. If you didn't know X is first order, you wouldn't be able to do this, okay? You wouldn't know, you cannot guess, right? It's because we know that X is first order, so times 2 will have an effect of times 2 on the rate as well, okay? So the remaining times 4 must be the effect from changing Y. Can you see that? So what can you conclude about the order with respect to Y? 0 first, second. Second order. Okay, so for reactant Y, compare between experiments 2 and 3, the rate goes up by a multiple of 8. Okay, 8-fold. We know X is first order. Therefore, since X is doubled, that will double the rate as well. So the effect of Y on the rate must be to quadruple it. Okay, so this is the explanation in mathematical-ish form, and this is the explanation in words. Okay, so make sure you copy both. Okay, so as Y is doubled times 2, the rate goes up by 4 times 4. And please also copy this down. How have I broken down that fold of times 8 into 2 effects? Okay, the red one is the effect from the X, and the blue one is the effect from the Y. So we say this, we call this a combined effect. Ang, are you copying this down? Okay, good. Oh, we have 10 minutes left. Really, I feel like time really does go fast in online class. Don't you think?
Corona time.
Who said that? Who was it? Corona time, Corona time. Okay, if you're done copying this down, then you can start writing down the overall rate equation. Now that you know that X is first order and then Y is second order, write down the overall rate equation. By the way, for reactant Y, you can also use experiment 1 and 3. Okay, no problem with that. But it's just that your X goes up by 4, your Y goes up by 2, your rate goes up by, let's see, 2.4 divided by 0.15. It goes up by 16. I hope you know how to find the fault. You just have to divide the big number with a small number. Okay, if you're wondering how I got by times 8, you take 2.4 times 10 to the power of minus 6 divided by 0.3 times 10 to the power of minus 6. So you just divide the bigger number with the smaller one. Okay, I have 7 minutes left. Can I move on?
Yes.
Okay. Moving on to the rate equation. Okay, your rate equation must include K, which is the rate constant, times by concentration of X to the power of 1 because it's first order, and concentration of Y to the power of 2 because it's second order. Okay, I know you have a lot of space for rate equation, but it's just that, right? This brings us to the next part, which is calculating the numerical value of a rate constant K. Okay, so calculating rate constant K for this reaction, we can choose any of the experiments 1, 2, or 3 because what did I say about rate constant? They are the same. They are constant for as long as the temperature is the same. Okay, remember K is the same for all experiments 1, 2, and 3 as long as the temperature is the same. So how do you find K? You rearrange. Okay, you rearrange your expression. Your rate, you can just choose one experiment. Easiest is to use experiment number 1. Your rate is 0.15 times 10 to the power of minus 6. Your concentration of X is 0.05. Your concentration of Y is 0.1 square. Make sure if you use the rate of experiment 1, the other concentrations must be from experiment 1 as well. Okay, do not mix them up. Don't take the rate from experiment 1 and then the concentrations from experiment 2 or experiment 3. Please just stick to one experiment. Okay, don't forget to work out your units, right? To work out your units, remember that the units for rate is mole per dm cube per seconds. Divide by the number of brackets you have. Okay, for X, that's only one bracket, so that's 1 mole per dm cube. For Y, you have to square it. Therefore, you square the mole per dm cube for Y. And then you can cancel out the mole per dm cube. You carry up the mole per dm cube square to become mole to the power of minus 2, dm to the power of positive 6, square, second to the power of minus 1. Right. Any problems so far?
No.
Are you calculating your rate constant?
Yes.
Okay, you should get, okay, so that's your units, mole to the power of minus 2, dm to the power of 6, second to the power of minus 1. We have about 3 minutes left. Okay, so your answer for the rate constant should be 3 times 10 to the power of minus 4 mole to the power of minus 2 dm to the power of 6 second to the power of minus 1. Okay, it doesn't involve any complicated calculations. Any questions so far, everyone?
No.
Okay, so you have questions on page 8 to do, example 3 and example 4, and from exercise 8.1. Okay, I'll WhatsApp you later on for your homework because tomorrow is Friday, so you will have time to do. Is that okay with everyone?
Yes.
Does everyone have anything
Yes.
important, more important than chemistry to do tomorrow on Friday?
No.
Isa, what about you? What are you doing tomorrow on Friday? Sleeping.
What, miss?
Do you have anything that is more important than chemistry for you to do tomorrow? If not, then you can do your homework. This is so sad. Sleep, praying, go temple. No, isn't the temple closed? Right. Okay, then. If there's no problem, no questions, you can go now.
Math.
Okay? Isa, you okay?
Thank you, miss.
Right. Thank you, everyone. You may go now.
Thank you, miss.
You're
Bye,
welcome.
Thank you, miss.
You're welcome.
Thank you, teacher.
You're welcome.
Thank
You're
you.
welcome,
Thank you,
Mukti.
miss.
You're welcome, Isa.